Hello, this video is going to talk about creating cross tabulations and normal transformations in IBM SPSS, and both of these are probability topics, uh, dealing with both categorical and continuous variables. And so I'm working with IBM SPSS, and I've opened the General Social Survey, the GSS, which is a data set you can download from the National Opinion Research Council. If you Google that, you should be able to find it. So what we're going to do is create a cross tabulation here, and I'm going to be looking at sex differences in terms of attitudes about whether or not people should have to have a permit to own a gun. All right, so uh, this is going to be a cross tabulation. So analyze descriptive statistics, crosstabs, and you can see I've already brought these in. Uh, if you right click in here, you want to show display variable names and sort alphabetically so you can find what you're looking for. And the variable for sex will be down there in the S's, and the variable for gun law will be in the G range of the variables. So just bring those over. And then in cells, we want to choose column percentage. Okay, and that's going to give us what we need for our interpretation. And what we're going to be looking at is, the percentage of male and female respondents who favor or oppose gun laws. All right, so there's the result. And we can see about 62.8% of males favor requiring gun permits, while 71.3% of females require it. And so there's an observable difference of about 9%, a little less, between males and females. Another way of saying that is the odds of favoring gun permits are higher for females than for males, right? About 7 out of 10 females favor it, so it's a 71% probability. I know it's kind of an unusual way of talking about it, but when we're looking at probability with categorical variables, that's really all we're talking about. All right, what about with continuous variables? And for this, we're going to do a little exercise of transformation. So I want to look at the variable for age. So I'm going to just quickly bring myself up to the age variable here. Okay, and I'm going to just right click this row number 23. And you'll notice one of the options there is descriptive statistics. It's a great little shortcut. So I'm going to click that, and right there it gives me the mean age of the sample and the standard deviation. So the average person is 52 in the sample with a standard deviation of 17.2. So when we're talking about probability with continuous variables, we usually have to look at a probability distribution. And for this, we're going to be looking at the z distribution. And that means we're going to convert the variable for age in years to a standard distribution, where the mean will become 0. And we'll have 1, 2, and 3 standard deviations accounting for about 99% of the entire age distribution. Okay, so how do we do that? Well, we come up here, transform, compute variable. Now what I'm going to do is I'm going to create a variable called age z. So that's the z distribution for age. Right? And the formula for converting that is going to be the mean subtracted from age, right? So it's going to be the difference between the two, right? Divided by the standard deviation. So I need parentheses for this, and I'm going to type the variable name age, and I'm going to subtract the mean, which, as we saw below, is 52.16. So what that's going to do is it's going to locate each and every person in terms of their relative position to the mean. And we'll divide by the standard deviation, which we saw was 17.23. Okay, so if you were looking this up as the equation for creating a z-distribution, it's simply x minus mean divided by standard deviation. Okay, so I'm going to click OK, and you'll see it if you have your settings in such a way that it prints the syntax. And syntax is another way we can do our analyses, which allows us to not have to use this point and click menu system, but the menus are convenient. Right? But what you'll notice is you don't really see anything else in the output. But if you go over to the data view, go back to the data file, and if you're in variable view and you go down to the bottom, you should see a variable called age z. All right, and if you double click that, you'll see that the range is basically from -3 to +3, right? Because we know that plus or minus 3 standard deviations accounts for about 99% of the z distribution. Okay, so let's move this up. It's right next to that variable for age. Just kind of dragging and dropping it here. You can see I've done this before. So we can call this the normal distribution of age. And when you look at those side by side, right, I'm just going to get rid of the old one. There we go. All right, so if you look at age side by side to the z version, we just rescaled age to the z distribution. We can see that somebody who's 65 is 0.75 standard deviations above the mean, right? And if you find somebody who's 52, like this person, you can see they're right about 0, right next to the mean. Remember, the mean is slightly above 52. 53 is slightly over it, 0.05. And somebody who's really young or really old is going to be closer, like 89, 2.14. I don't think we have anybody much older than that in the sample. So in this case, a couple standard deviations captures the bulk of people. All right. So now we can actually look at the relative position of each person to the mean in terms of standard deviations, instead of having to kind of figure that out, conceptually by looking at their actual ages. Of course, the nice thing about an age distribution or a z distribution is that any variable can be converted to it, which makes everything on the same scale, which is really a useful way to interpret results when you're doing things like correlations or regressions. So what else can we do with this? Let's say we want to know what the probability is if we were to randomly choose a person from the sample, from a hat, right? Just randomly pick someone. What are the odds that person's going to be, say, 89? Well, we can just look up 2.14 on this z distribution table, right? And maybe at the 95% confidence level. So I've pulled up a z distribution table here, and we're looking up the value of 2.14. We need to start over here on the left column and go down to 2.1, and then you see that each subsequent decimal place is in columns. So if we come over to 2.14, we'll get a p-value of 0.0162. So the odds that we would just randomly pull an 89-year-old out of the sample is about 1.6%. So it's a pretty unlikely event, and that's because there aren't many people of that age, right? It's pretty unusual. And this is a mirror distribution, so negative 2.14 would be somebody who's about 18. It would be the same probability. Okay, so it works in terms of positive or negative value, since it is symmetrical. By going back and forth between the actual ages and the associated standard deviations and going to the z distribution table, we can figure out the odds of selecting anyone in terms of random selection from the sample. And that's how we go back and forth between raw data, standardized versions of that data, and probability. And those are the steps we have to go through to calculate continuous probability. Thank you.